Alright guys, so in this video we're going to describe or we're going to study the idea or how we would compute definite integrals when we have the equations of the curve in terms of parametric equations. Alright, so let's say that you have a curve, your favorite curve, and it's given in parametric form. As always, what my curves look like. What can I say? Not much imagination there. Unless you're going to evaluate, let's say, from a time equals a. So let's say that this is going to be x naught, and x naught is going to be equal to x at a times equals a. So you're going to be integrating on a time interval from a to b. So this right here, this time here represents time equals a, and you're going to have a times equals b somewhere here, and that's going to be your, I'm going to start by partitioning everything into n uniform time intervals. Just what it is, I suppose. My curve is oriented in this direction, and I will be taking this, it will be my xn, which is going to be x at times equals b. Okay, so I am going to partition my interval into my time interval into uniform intervals. So I'm going to grab a delta t, if you will, not that color. I'm going to grab a delta t, which is going to be just ti minus 1. Those are going to be my time increments. I'm going to start at time equals 0 all the way to time equals n. So now I'm going to partition. I'm going to find what those points are going to correspond to. So I'm going to have x1, x2, x3, all the way out to xn. And I'm going to draw a rectangle. Right sums are usually easier to do, so I'm going to go with right. And I'm going to start my sums there, and I'm going to continue like that. Okay? So what would be this delta x? This delta x will just be x for each one of them. So I'm going to suppose it's going to be delta xi is going to be xi minus xi minus 1. So I'm going to be taking x1 here, for example, x2, x3. So the delta x I'm going to be using, or the width of my rectangle, I still need that, right? I'm going to be computing area, so need width of a rectangle times the height. Well, the width is just going to be, say, in this case, it would be x3 minus x2, just the width of that rectangle. In general, the delta xi is going to be xi minus 1. All right, and that will also be written as x evaluated at ti minus x evaluated at ti minus 1. So I'm going to grab my delta t, and at each endpoint of my interval in time, I'm going to be evaluating the x's. That's going to give me these x's right here. Now, so what is the formula for my right sums in this case? My right sums would be the sum from I equals 1 to n of my delta xi. You see now the delta x is not uniform with respect to the x, it's uniform with respect to time. And then a f of xi. But I'm going to be a little bit careful here because I'm not evaluating a function f. My function is with respect to parametric equations. So I'm going to grab a yi. Just slight difference, but that yi is going to be the y. I suppose I'm going to write here where. Sorry about that. Yi is equal to y evaluated at ti. Okay. So what would yi be? It would be, for example, in this case, this would be y1. Y1 is nothing but the height of the curve at times equals 1, because the x is going to be x evaluated at t1. Now the y that corresponds to that point on the curve is going to be y at t1. For a second I was thinking I had done the wrong side, but no, I did not. Phew. That's why if you saw my face change, like, oh, it's because I thought I had done the wrong one. But no, it was all good. So now this one, for example, would be y2. And y2 is going to be y evaluated at t2, and so forth and so on. So this is going to just become, the area is going to be the limit as n goes to infinity of this right here, which is going to be written like this. Sum from I equals 1 to n of, let me write the yi first, and then let me write out this this delta xi. So I'm going to write it as x of ti minus x at ti minus 1. Am I still in? Yeah, I'm still in. Alright, so that's what we have. Now I'm going to do a little bit of trickery here. I'm going to have to write smaller. So let's write it as limit as n goes to infinity of the sum from I equals 1 to n, and I'm going to multiply and divide by something magical. Not very magical, but whatever, we'll call it that. This marker is starting to squeak. I don't like that. We're going to have to throw it away. I'll try to write quietly there. And you say, wait a second, there's no ti's anywhere. Well, I'm going to divide by them, and then I'm going to multiply times them, but I don't know if I have enough room there. I'm going to write it as delta ti, so I can fit it. Delta ti just being this quantity, ti minus 1. Oh, I wrote it up here. Perfect. All right, so now, if I pay attention here, this looks like a derivative. Now, it wouldn't be the derivative at ti or at ti minus 1, but the mean value theorem tells me that there will be a point within that interval where the derivative will equal this slope of a secant line. So this becomes, if I can fit it there, actually I'm going to move to the other side and write it there. So let me move for 1 second. I'm going to erase this and I'll be right back. Alright, so I'm going to continue with this, and I'm going to go ahead and take the limit. But I'm going to write one more thing. So as I was telling you, the mean value theorem tells me that there's a point where the derivative x prime will take that value. So I'm going to write it as I equals 1 to n, yi, and then this is going to be x prime evaluated at some t I tilde, if you will, which is just going to be a ti in between in this interval. That's all it is. Times some delta ti, which is what I wrote here. By the way, my delta should have been delta ti. Well, I took it uniform actually, now I don't remember. So when I take the limit here, this is going to then become the integral from a to b in time. You see, this is going to become your delta time, and this is just going to be your y of t. This is going to become your x prime of t, and then dt. So that is the formula that you will need for how you would integrate, or how you would find the area under the curve if the curve is written in parametric form. So your area becomes that right there, that integral. Alright, so let's do one example real quick, and then I think we can wrap this video up. Alright, so let's return to a very similar example than the one we did for the previous video, where we were talking about a projectile being shot horizontally at a height of, I said 100, but now for the numbers to work nicely, I'm going to use 64. Hope you forgive me about that, because if you use 64, then the projectile hits the ground at times equals 2. Much nicer than, say, the square root of 64 or 100 over 16. Much, much nicer. Oh, that's not too bad. That's 10/4. Okay, never mind. That was 2.5. Well, no need to change the numbers. Now I did. So anyways, I'm fighting with myself, you notice? So what that parabola will look like is just going to be that at 64 here times equals 2 here, and I'm trying to locate this area by using this formula here. So the area, according to my formula, now in parametric form. Now, 1 second, let me just back up. If I wanted to compute it without the parametric form, I would have to solve for the parameter here. So write x over 100 equals t, substitute in, and then do my fundamental theorem of calculus. But now I would have to go from, now this is times equals 2, my bad. The height or whatever the distance it travels here would actually be 200, because the x coordinate would go 200 feet. So you'd have to evaluate the linear integral from 0 to 200, and you would have to use the rectangular form. But we're going to do it with the parametric form, which is then I don't have to solve for anything. I just plug it in. Now my time goes from 0 to 2. All right, and now I'm going to do y, which is going to be negative 16t squared plus 64 times x prime. X prime is just 100 dt. And now it's just a matter of integrating. So I probably should keep that 100 as a common factor. Then I go ahead and integrate. So this is going to be negative 16 t cubed over 3 plus 64t, and I'm going to evaluate between 0 and 2. And then it's just a matter of doing the numbers, whatever that will turn out to be. Sorry about the squeaky noise. So it'll be 100 times then 16 times 8. That's going to be 64 times 2, 128. So negative 128. I'm just evaluating at t equals 2 over 3 plus 64. I evaluated 2, 128. So 164t evaluated 2, I should have said. And that is going to be 2/3 of 128 times 100. So that's how you would compute an area using your parametric equations. So I'm going to stop right there, and I hope you enjoyed the video. Thank you for watching, and I'll see you in the next one.